Good evening, everyone. So today we'll be taking the class 11 physics, and the topic we'll be discussing today will be about the basic mathematical tools of class 11 physics. So this topic will be purely based on the basic mathematics. So it will be totally based on the pure mathematical tools that we'll be using in different chapters of the physics, be it in class 11, be it in class 12. So these are the very important topics that should be always handy for class 11 physics or class 12 physics. And one of the important topics of the basic mathematical tools is derivatives and integral calculus. Derivatives and integral calculus. So we'll be first discussing about, we'll be giving a brief revision about the derivatives of different functions, how the derivatives work for the different functions, and what are the different tools for the derivatives, and also how we can apply these derivatives in different questions. Suppose that I have a Cartesian plane. मेरे पास एक Cartesian plane है. Why explain? And in this plane, there is some curve like this. और हमें डेरिवेटिव डिफाइन करना है. Derivative, we mean the dy upon dx. How geometrically we define the derivative of a function. एक फंक्शन का हम डेरिवेटिव कैसे निकालते हैं और उसका जियोमेट्रिकल मतलब क्या है. सपोज हमारे पास ये एक y एक्स प्लेन में एक कर्व है, तो मैं एक पॉइंट लेता हूं, पॉइंट P, और इस पॉइंट P का मैं टेंजेंट ड्रॉ करता हूं. इस पॉइंट, दिस इज द टेंजेंट ऑफ दिस पॉइंट P. This is the tangent on this curve at point P. So derivative actually, what it actually represents, it represents the slope of a tangent at some point on a curve. कोई भी कर्व हमारे पास हो, तो अगर हमें इसका स्लोप बताना है कि इस किसी भी पॉइंट पे इस कर्व का स्लोप कितना है, so what we'll do is that we'll calculate the derivative of that function at that particular point. So suppose that the coordinates of this point are x naught comma y naught. तो इस पॉइंट पे, अगर पॉइंट पी पे हमें ये बताना होगा, ये देखना होगा कि इस पॉइंट पी पे इस टेंजेंट का स्लोप कितना है. तो हम क्या करेंगे, हम इस फंक्शन का, या फंक्शन मान लो कि y कोई फंक्शन है x की, हम क्या करेंगे, इसका डेरिवेटिव निकालेंगे इस पॉइंट पे, दैट्स dy अपॉन dx at this point at x equal to x naught. This will give us the slope of y at point P. Point P. Suppose that this tangent makes an angle theta here. So this dy by dx at this point P, dy by dx at this point P, that is at x equal to x naught, will also be equal to tan of theta of this angle which this tangent at point P makes with this positive x-axis. Slope actually means, slope tells us about the steepness of a curve. Steepness of a curve. And dy by dx, इसी को हम डेरिवेटिव कहते हैं, और इन particularly we call it as first derivative. First derivative. और अगर इसी फंक्शन का हम twice derivative लेते हैं, let's we take a derivative 2 times, call this as second derivative. And suppose that dy upon dx, that's the derivative on a curve at a particular point, comes out to be 0. Comes out to be 0. We can say that the slope of that point, slope of that tangent at that particular point on a curve is 0. Is 0. कहने का मतलब ये है कि उस पॉइंट पे उस वो टेंजेंट जो है एक्चुअली 0 एंगल बना रहा होगा पॉजिटिव एक्स एक्सिस के साथ, मेकिंग ए एंगल इक्वल टू 0 विद द पॉजिटिव एक्स एक्सिस. स्लोप हमारा 0 भी हो सकता है, इसी पॉइंट पे स्लोप 0 भी हो सकता है, एंड दिस स्लोप कैन बी नेगेटिव ऑल्सो, और ये स्लोप हमारा पॉजिटिव भी हो सकता है. The slope can be 0, negative as well as positive. Suppose that मेरे पास यहाँ पे 3 कर्व्स है. This is the straight line, and this is one more curve, and this is another curve. This is curve number 1, second and third. इन सारी कर्व्स पे क्या है, एक इम्पोर्टेंट, अगर हम सारी कर्व्स पे किसी भी पॉइंट पे टेंजेंट डालें तो tan of theta उन पॉइंट्स पे जो है इट विल बी ऑलवेज पॉजिटिव. सो ऑल these कर्व्स ये सारी कर्व जो है पॉजिटिव स्लोप को रिप्रेजेंट करती है. अगर हम इस पॉइंट पे सपोज टेंजेंट ड्रॉ करते हैं, the tan of this theta will be once again positive. और अगर इस पॉइंट पे हम इस कर्व पे टेंजेंट डालते हैं, इट बी वंस अगेन पॉजिटिव. और अगर हम ये पॉइंट पे इस कर्व पे ये पॉइंट चूज करते हैं, द टेंजेंट, suppose this makes an angle of theta 3 at this point, and this tan of theta 3 will be again positive, yeah, that is greater than 0. So these are the possible curves which can have the positive slope. And similarly, अगर हम इस तरह से स्ट्रेट लाइन को ड्रॉ करते हैं और इस तरह से एक कर्व प्लॉट करते हैं, and this is the third curve like this curve number 1, 2 and 3. We can clearly see that all these curves are with negative slopes. That is, the derivative at any point on these curves will be less than 0. It will be negative. it will be negative. Then what does this represent? This represents a slope equal to 0. इसकी क्या क्या पॉसिबिलिटीज है, कैसे कैसे एक स्लोप 0 हो सकता है जनरली. सपोज मैं कर्व कैसे प्लॉट करता हूं, लाइक दिस, which is a parabola, which is a parabola. If I choose this point, suppose this point, the coordinate of this point is x1, y1. If we draw a tangent at this point, suppose I'm drawing a tangent at this point, that's at x equal to x0. You can see the tangent is parallel to the x-axis. Tangent is parallel to the x-axis. That is, its slope is 0. Slope is 0. This is one of the possibility. Another possibility of slope being 0 is, suppose I just draw a parabola like this. This is the downward parabola and this is the upward parabola. And this is the point, and I call this, suppose the coordinate of this point is x2 comma y2. Now again, if I draw a tangent at this point, you can clearly see that it makes an angle of 0 with the x-axis. So tan of 0 will be once again 0. So slope of this tangent is once again 0 at this point. So what does this value represent? This point represent? This point is a minimum point of this curve. This represents a minimum. This is the point where the value of this y is minimum. And this is the point where the value of this y is maximum. So slope 0 gives us two conditions. If at some point x0, at some curve, the derivative is 0, it means that either the point represents the maximum value of the curve or the point represents the minimum value of the curve. Now, how can we check whether the particular, if at some point the value of the curve, the value of the derivative is 0, how can we check the curve has a maxima or minima at that point? Then we have to check the second derivative for this curve. We have to go for second derivative test. We have to check the second derivative for this curve. If the second derivative of this curve at that point where the first derivative was 0, if this comes out to be greater than 0 or positive, if this comes out to be greater than 0 or positive, then the point will represent a minimum. And similarly, at this point where the first derivative is 0, that is at x equal to x0, comes out to be negative, it's less than 0. Then the point will represent a maximum. That's how we can check whether a particular point represents a maxima or minima if at that particular point the derivative of a function is 0. And this is an important application of the derivatives that we very usually use in physics to calculate the maximum value of different physical quantities or the minimum value of different physical quantities. So these concepts will be very frequently used. There is one more important conclusion about these second derivatives that we'll discuss. if the second derivative comes out to be positive for any curve, the concavity will be always up. What do you mean by concavity will be always up? Suppose that I have this curve like this. Let me select this as point A, and this is point B, and this is point C. From A to B, we can clearly say the concavity of this curve. This curve shows some concavity. If you have studied about or learned about the concave mirrors and the convex mirrors, so this is how we'll assume as if this is in case of spherical mirrors, we have a silvered surface, and then we define the two terms, the convex mirrors and the concave mirrors. So this is the concavity of this curve from A to B. But we can clearly see that the concavity of this curve is down. It's concave down. If the curve is concave down, so we can clearly see from point A to B, the second derivative of this curve at any point between A and B, it will be less than 0. It will be less than 0, not greater than 0. It will be less than 0. It's concave down, and this from B to C, concavity is up. So its second derivative will be greater than 0. So these are the two important conclusions about the derivatives or the second derivatives. So first important point about the first derivative is that it tells us about the slope of a curve at a particular slope of a tangent on a curve at a particular point. And one more point, if the first derivative comes out to be 0, either that point will be representing the maxima or the minima. And then there is a test. How can we determine whether the particular point represents a maxima or minima? We do a second derivative test. If the second derivative of that function at that particular point where the first derivative was 0 is positive, then it will represent a minima. If that is negative, if second derivative is negative, then it will represent a maxima. And one more important conclusion is that if the second derivative of any curve is greater than 0, it's positive, its concavity will be always up. If its second derivative is negative, its concavity will be down. Likewise, in case of parabola, you can see in case of parabola also, suppose we have a parabola here. Its concavity is up. So I can clearly say that second derivative of this parabola will be a positive. And similarly, if we plot a downward parabola like this, this is our downward parabola. Its concavity is down. Concavity down means the second derivative of this function, that's the second derivative of this parabola will be always negative. And we can also conclude from this that if the function is concave up, If the function is concave up, it can have a point of local minima. If the concavity is down, it can have a point of local maxima. Suppose that we have a polynomial function like this, y equal to x raised power n. We know that the derivative of this function, that is x to the power n with respect to x, is nothing but an x to the power n minus 1. An x to the power n minus 1. So this is the derivative of a polynomial function. For example, if y is varying as a function of x as x cube, right? Y as a function of x is y equal to x cube. Its first derivative will be dy upon dx. It will be d upon dx of x cube. So power will be down. That's 3 x raised power 3 minus 1. It's 3x squared. And similarly, if we calculate the second derivative of this function, that is d by dx of 3x squared. So it will be nothing but 6x. It will be nothing but 6x. Similarly, if we have function like this, y equal to 3x squared plus 2x plus 1. If we calculate the derivative of this function, that's dy by dx, will be d upon dx of 3x squared plus 2x plus 1. We'll just distribute this derivative, right? So it will be d by dx of 3x squared, d by dx of 2x, and d by dx of 1. So once again we'll use the same property, this one, कि हमारे पास x to the power n का डेरिवेटिव बराबर होता है nx to the power n minus 1. So we'll get 6x plus, since this 2 is a constant, 2 is a constant, so it will not change. Constant function जो है, constant function तो कभी change ही नहीं होगी. Constant function का हमेशा डेरिवेटिव 0 होगा. So this 2, but अगर यही constant function is in multiplication or division with some function, with some variable, then ये constant function जो है derivative से बाहर आ जाएगा, and we will take the derivative of that variable. And here we have only pure constant. The constant का derivative हमेशा 0 होगा, because constant will not change. It itself says that I'm constant, that it won't change at any cost. So its derivative will be 0. So finally we get 6x plus 2x. Sorry, 6x plus 2. Derivative of x with respect to x will be 1, right? So it will be 6x plus 2, and this is the final answer for this question. This is the first derivative. Similarly, we have different functions like d by dx of e to the power x. Its derivative will be e to the power x. We have d by dx of log of x. Its derivative will be 1 upon x. And the derivatives of different trigonometric functions. Like we have sine of x. The derivative of the sine of x will be cos x. And derivative of cos x will be minus sine x. And similarly, if we find the derivative of tan x, it will be nothing but sec square x. So we can calculate the derivatives of different functions. And these are some of the examples, very important examples, uh, that we should know the derivatives of all these functions. Suppose that we have to take the we have a function like this, y equal to e to the power ax, and we have to find first derivative of this function. What we will do is that initially we knew that the derivative of e to the power x is e to the power x, but we have here e to the power ax. So we'll take the total derivative of this function. It will be derivative of e to the power ax. It will be e to the power ax, and the derivative of this power, that's ax, that will be d by dx of ax. So we'll get e to the power ax. The derivative of a is a constant, a is a constant, a is a constant, and this a will come out of this derivative, and the derivative of x with respect to x will be 1. So we'll be left with nothing, a e to the power ax. So this will be the derivative of e to the power ax. That's a e to the power ax. Similarly, if we have a function f of x of this form, function of this form, then we have to use a rule what we call as product rule. Product rule. What is that product rule? That d by dx of f of x, or we can also call it d by dx of y, that's uv. We'll take one function out and take the derivative of another, and now we'll take p out and take the derivative of u. That's how we use the product rule if the function is of the form u multiplied by v. This rule is very important. For example, we have y equals x square sine x, and we have to take the derivative of this function. So there are two functions. This is one, suppose this is u, and this is another trigonometric function, we call it v. So how will we calculate the derivative of this y? Using the product rule. So our product rule says take the derivative of one function and take another function out of the derivative, that's x square sine x upon dx, and sine x x square. The derivative of sine x is nothing but cos x. The derivative of sine x x square is nothing 2x. Once again using the same formula, that d by dx of x to the power n is nothing nx to the power n minus 1. And similarly, suppose we have function f of x, it's of the form of u by v. It's of the form of u by v. So what we'll do in this case, We call that a quotient rule. We use a quotient rule for this function. The function is of this form. We'll take this function out, take the derivative of u with respect to v minus u and the derivative of function. We'll take the derivative of u with respect to x, and we'll take the derivative of v with respect to x and keep this u outside the differentiation and upon u square. This rule is what we call as quotient rule. This is the quotient rule to calculate the derivatives if the functions are of the form of u upon v. For example, we have a function like this, 4x upon x square minus 2. This is one function of the form of u, and this is another function which is of the form of v. So how will we calculate the derivatives of derivative of this function? What we'll do is that we'll use the quotient rule. We'll take this v outside, that's x square minus 2, and then take the derivative of this 4x with respect to x. Then we'll take this 4x outside and take the derivative of x square minus 2 with respect to x and the square of this x square minus 2. So x square minus 2 and derivative of 4x will be 4, and the derivative of x square minus 2, once again the derivative of this minus 2 with respect to x will be 0. It's a constant, it will go to 0, and the derivative of x square will be 2x, and we'll be left with x square minus 2 whole square. So it will be nothing 4x square minus 8 minus 8x square upon x square minus 2 whole square. So it will be minus 4x square minus 8 upon x square minus 2 whole square. So what we can do in this function is, if we take 4 outside, okay, minus 4, so it will be x square plus 2. That's the final form of this derivative. So this is how we calculate the derivatives of functions which are of the form of u upon v. Can take one more example. Suppose we have a function like y equals sine x upon cos x. That's nothing but the tan x. So how will we calculate the derivative of this tan x? We'll use u upon v rule, d by dx of sine x upon cos x. So once again cos x will be outside. We'll be taking the derivative of sine x minus sine x will be outside the derivative, and we'll be taking the derivative of cos x upon cos square x. So sine x has the derivative cos x, so it will be cos square x, and the derivative of cos x is minus sine x, and minus minus will come out to be positive, so it will be sine square x. upon cos square x. We know that cos square x plus sin square x is nothing but 1. So this term numerator will go to 1, not 0. This will go to 1. We'll be left with 1 upon cos square x. So 1 upon cos square x, 1 upon cos x is sec x. So it will be nothing, sec x square. So derivative of tan x is nothing. It's sec x square or sec square x. So this is the final result that we get when we take the derivative of tan x. I think this is enough for today, and we'll be meeting in the next class, and we'll be dealing with the questions of maxima minima, and then we'll be discussing with the integrals and their applications, and we will be also discussing some of the applications of the derivatives. Till then, take care and goodbye.